This complex numbers solution is for the 2020 paper. It's paper 1, question 2, and it's just the first bit of it. So we're asked to find z1 and z2 if iz1 equals minus 4 plus 3i and 3z1 minus z2 equals to 11 plus 17i. And we want to find it in the form a plus bi. And they also mention the fact that this is a simultaneous equation. And that's true because I've got two equations, and you can see here I've got z1 and z2 in that second equation. But don't try to approach it exactly the same way that you'd approach a regular, straightforward algebra simultaneous equation necessarily. Probably the easiest thing to do here is actually just to find your z1 first of all. So to do that, I'm looking at the first equation, and you can see that I've got I z1. So I can get z1 by itself by just taking the I across and dividing it into the right-hand side. And now we can sort this out using complex division. So don't forget, for complex division, what I need to do is I need to look at the denominator, I need to find its conjugate, and then multiply top and bottom by the conjugate. And this is actually quite a nice one. So the conjugate of I is just going to be minus I. So I'm going to multiply this fraction top and bottom by minus I. So what's that going to give me? Pause the video here while you work this out yourself, and then try to simplify z1 into the form a plus bi. Then press play and see if you're correct. Okay, so on the numerator, we're going to have 4i minus 3i squared, and I'll come back to that I squared in a second. And in the denominator, I'm just going to have minus I squared. Now, don't forget the key fact in complex numbers, which is that I squared is equal to minus 1. So whenever I spot an I squared, I want to replace it with a minus 1. So I've got a couple of those going on here. Just watch out there in the denominator for the double minus, so minus minus 1. And then tidying that up, I'm going to get z1 equals 4i plus 3, and then it's simply a case of just writing it as a regular complex number in the correct order, a plus bi. So the over 1 I can kind of disregard essentially. And I'll put the real part, the 3 first, and the 4i at the end. So that's z1 sorted out, and now we go on to figure out z2. So to do that, I'm going to look at the second equation, which is this one here. And of course, it contains z1 as well as z2. So I can actually go to where z1 is located there in that equation and just substitute in the z1 that I've just found. So having substituted that z1 into that equation, I'm ending up with 3 bracket 3 plus 4i minus z2 equals 11 plus 17i. I want to multiply out my brackets, and I'm going to want to get z2 to one side and everything else to the other side. So looking at it at the moment, the z2 that I have is negative. I really would prefer it to be positive because I don't want minus z2, I just want z2. So I'll bring that across to the right-hand side and everything else over to the left. So 9 plus 12i can stay put. The 11 and 17i can come over and become negatives. The z2 can hop over to the right and become a positive, and now it's simply a question of tidying up like terms here. And again, try to put the real part first and the imaginary part second. So we're going to have 9 minus 11 first of all, giving us minus 2, and then 12i minus 17i, giving us minus 5i, and that's my complex number z2. And so there are my two solutions, z1 and z2.